Is anybody nothing, who did not receive the invite to OneNote? Anybody? You didn't? See me after class, I need your email. I emailed the whole class. You should have gotten, it might have been your spam folder though. I'm going to warn you, sometimes it ends up there. How are we doing with the lecture?
I sent you the link today.
You did?
Yeah.
When?
About 12 o'clock. I can get with you afterwards to make
I
sure.
didn't, that explains it. I've been busy. I had time to show you that. All right. Well, today, are there any questions at all about the homework at all? Yes? 1.1. 1.1? All right. Now, can you briefly just tell me what it is?
Yes, sir. It's the x is going to be 2t plus x.
Oh, hold on. X. Go ahead. Parentheses.
2t plus.
2t plus
6.
6. And what is x of t? Is it a functional form or is it a picture?
It's a picture.
Can you describe the picture for me?
You have on the t-axis, you have the points of 2 and 6 as a triangle from 2 to...
Hold it. 1, 2, 6, and go ahead.
So it's a triangle where...
Starts at 2?
Where does it center?
Where's
it
the center?
centers at 4. But it's just upward slope from 2.
From 2 to 4?
2 to 6.
2 to 6. Straight up? Like this? Like this?
Yeah.
Yes.
Okay. So, is this a 1-to-1 or what's
And the top value is 4.
All right. So this is 4. Now this range is 4 as well, right?
Yes.
Therefore, this slope is 1-to-1. Follow me? Goes up 1, over 1. That means an equation for this line right here, if we were to write an equation for this line, pay attention to this. A lot of people mess this up. If you're going to get an equation for a line, then we'll just call this x of t here. X of t is equal to a slope, if it's a straight line. A is going to be the slope in this case. A lot of times it's mx plus b. I'm just using a here. It's a, the actual horizontal variable is t, so it's at plus a constant b. That's the intercept. Now here's how you do this. The slope is already known as 1. Isn't it, class? Y'all understand how I got that? I look at the rise on that thing. Over 1, up 1, slope 1. I can take a derivative of that thing and you find it's 1 with respect to t. So I can get rid of a and just call it t. Now the b-intercept, people mess up all the time. I'm just telling you this. They do. A lot of engineers are so casual, they don't even pay attention to how to write an equation. You can't do that. You have to be very focused about these things. Equations are straight lines, ellipses. If you aren't, everything else you do is for naught. You got to get the first things right. So to get this intercept, what you always do is look at the point where the function is 0. Where is it 0 here? At 2, isn't it? Right? At 2, the straight line has a 0 value. Correct, class? So you put 0 over here is equal to 2 plus b. And what must b be by looking? Minus 2. Follow me? Everybody understand it? I know it seems trivial. All right? You get this in grade school. But people mess this up routinely that are engineers because they're too casual. It's like, I can't be both. If you don't get this right, everything else is wrong. Therefore, this equation for x of t is just t minus 2. But it only is what? Has values between 2 and 6. Now, you could do it a couple ways. What I'm going to do is use the u of t here. That would be u of what? T minus 2 is where it starts, correct? That flips the switch, it's on, right? I want to extinguish it at 6, so minus u of t minus 6. That would do it. We could use a pulse function. I chose to use u of t here for simplicity, for what I'm up to. Everybody got that, class? Next, this is one way to do it. There's 5 or 6 ways to do this. Let me show you. Now what you do when you do these things, you factor out. What you want to do is just have x of something times t. Let me show you exactly what I'm talking about. I want x of 2 times quantity t plus 3. Are you with me on that? So I have t by itself inside that parentheses, the second set. With me? The 2 is a scale factor that I'll explain. Everybody with me so far? Now just watch this. So here's how I do this. First I'm going to take a look at simply what x of 2t is. Are you with me? Just x of 2t. Not with the plus 3, just x of 2t. Got it, class? Now watch. What does this become? If we just take wherever the t was, we replace it by 2t. Correct, class? So mathematically, it would become 2t, right, minus 2 times quantity u of 2t minus 2 minus u of 2t minus 6. I'm doing it mathematically for a reason. I'm showing you how to break these things down and develop the final form. Understand, everybody? I ignored the time displacement. I just want the scale factor first. Now when you look at this, follow me. Can't I function or factor a 2 out of these two things? You all agree with me there? Yeah. So I'm going to. Right? Now I'm going to factor a 2 out of there. With me? Keep watching, you're going to see what happens. Now I'm going to factor 2 out of the last one. Are you with me? Everybody? All right, let's take a look at this for a second. First, where does this function turn on? Just look at this right here. It's where what? Where this argument is 0, correct, class? Where is this argument 0? Forget the 2. It doesn't do anything. What are you looking at? T minus 1 is 0, correct, class? Or t is equal to, say it? 1. 1. So now I'm going to go over here. And this is going to be my x of 2t here. And I'm going to call that really x2 of t. This is a second functional. I'm going to show you how to think about this. Now, I know it starts at 1, right? Where does it get extinguished at? Where t minus 3 is 0, right? Which is t equal to 3. You'll notice what happened here. The range used to be 4, right? Now it's shrunk down to 2. Do you all see that? The actual range where it's on. Everybody see that? So now between 1 and 3, it's on. This right here, right, when t is 1, this is 0. Is it not, class? The t minus 1, 1 minus 1 is 0, correct? What is the value when t is equal to 3? 3 minus 1 is 2, correct? Times 2 is 4. So it's going to go up 4. And that's what that function looks like. Do you agree with me? I call that x2 of t. It's really the first function of x of 2t, right? With me? Now, watch. This function here, right, is really what? It's this function, only it's really x of 2t quantity plus 3, which is my x2 of just what? T plus 3, isn't it, class? I called x2 my x, right? Y'all with me on this, class? I'm not trying to confuse you. I'm trying to do this methodically so you see how I'm building these things. I'll show you how to just look at it in a second and get the idea. But are you with me on this? How many see this? Be honest. If you got, it should be pretty obvious what I'm doing. I'm simply defining things mathematically first. Yeah? Oh, you do see it? Yes. Okay. That mathematically first. You all agree with that part, right? Now I said, when I take a look at this thing, since I know this is what I'm up against, I want just x of 2 times the quantity t first. And then I'm going to add 3. Understand, class? All right, now, what happens since this is x2 of t is this function right here, is this function right here that I've defined, right? Correct? This is x2 of t, correct? Agree? Now, listen carefully. What happens when I add 3? Instead of the argument being t, now it's t plus 3. Just watch. I think you see it. We're going to do it mathematically. You'll see what happens in a second to the actual picture. So when I put, instead of t plus 3, what happens to this? T plus 3 minus 1 is t plus 2. Correct? Over here, t plus 3 minus 1 is t plus 2, correct? Everybody? So this is t plus 2. Right? And over here, t plus 3 minus 3 is t. So now this is the actual mathematical description of what's going on. Do y'all agree with me? Y'all see this? I'm trying to do this mathematically so it becomes easy for you to see mathematically. Then I'll show you graphically how easy it is. Now I'm going to leave this up here. This is x of 2t. Now what I'm going to do, I think I can do it right under here. Hopefully. Now I'm going to do x2 of t plus 3, which is my x of 2t plus 6. Is it not, class? Everybody agree with that? All right, what does that look like? Whenever you have x2 of t plus 3, remember what happens. What if it was x of t minus 1? What would happen to this whole thing? It would shift over by 1, right? What if I had x of t plus 1? It would shift this way by 1, correct? If it's by 3, what happens? It shifts the whole thing over by 3, correct, class? So I'm going to do it down here. I think you're going to see it. Just do this. Here's the end of it, right? The end was at 3, correct? If I go over 3, the end is now at 0. And the height is still 4, isn't it, class? You agree with me? And now I just what? Now I go over 2 and take it down to 0 minus 2, correct, class? Just go over 2 right here. And now this is the function. We did it mathematically by expressing everything, just so you see. I hope I'm answering your question from a mathematical perspective. Here's how I do these things. This is the way I do them. I take a look at this picture right here. And I see, well, they want x of 2t plus 6. I forget about the 6. I'm telling you how I do this. I forget about the 6. I want to see what that looks like. Right? Well, what it's going to do is what?
It's going to shrink.
It's going to shrink the width by a factor of 2. You all see that? What about the center? What happens to the center? Just take a look. Originally, right, it was at 2. But when we do this factor of 2t, right, what happens? Now it divides this axis right here, divides the values by 2, correct? Now we start at 1 and we end at 3. Do you all see that, class? So I know instinctively what's going to happen to this waveform is going to be the same height, but now the width is divided by 2 because there's a 2t, right? And the actual scale is moved by the original scale divided by 2. I hope I'm answering your question. This is the way I do them. I look at the picture. I don't care about it. I don't write mathematical statements, right? But then I said to myself, now this function is really a second function which I call x2 of t, but I've got to add the 3. Follow me, guys? What do I do when I add 3? I know if I subtract 3, I'd move to the right by 3. Add 3, you move to the left by 3. Follow me on that, class? And that's the game ball on this one. I'm glad you asked that question, because engineers do 2 things routinely. They hate thinking about trivial things like equations for lines, number 1. The second thing is they hate thinking about moving left or right by incremental values. They're looking for the big, something massively important, not trivial stuff, but this is real important. Did I answer your question? Any other questions about the homework? You okay with that? Any other questions? I hope, please, just keep up with the homework. What he just asked, this problem, is the beginning of nightmares if you don't keep up. Trust me, this gets really complicated really quick, and if you're not on point all the time, you're really asking for trouble. I don't care how bright you are. I've had people that were basically just about perfect ACT scores, perfect SAT, crash and burn. So it's not one of these courses you casually walk through. I don't care what your friends think. I'm being honest. Next, any other questions? I gave you, it was graphical, right? All the homework was basically functional forms, graphing, either writing in terms of a graphic or in terms of mathematical functions, some graph or graphing something that was mathematically stated, right? Do you all have access to the answers, the solutions? All right, did they all make sense to you? All right, now level with me now, and I will not criticize you, I'll not hold it against you. How many did the homework? All right. All right, please try to do the homework. I'm not going to rant every time. I'm not a fire and brimstone preacher, but I know what happens in this class if you don't. And I absolutely hate having to deal with people crying in my office and throwing firebombs at me. It's football season. I got more important things to love. Speak of that, where are we ranked these days? I haven't checked.
9.
In the country, we're 9? Where are we in the SEC? Are we over 3? Are we 3? Bama, all right.
Alabama and Georgia are both ahead of us, maybe.
What about LSU?
I think they're behind us.
Well, if we're 9th in the country, that's good, but the SEC is really the country. You know? People that win it generally win everything. All right, now, today's lecture is going to be a tough one. So, however you do it, focus. This is, first I'm going to start with the baby steps, but then we're going to get right into the brute force brutal stuff. First I have to talk about what systems we're talking about generally. Now I'm going to tell you this. There are a lot of systems that are very, very complicated. Nonlinear systems, things that allow non-causal systems that you're going to find out about. Our entire coursework here is dedicated to the most common systems that you run into. They're called linear time invariant systems, LTI. Linear time invariant systems. All right, now, what is a linear time invariant system? Which is a good question. The way we deal with systems, because we could be talking about electrical systems, we could be talking about mechanical, we could be talking about chemical, anything. There's something that is an input, there is something that acts on that input, and then there is an output. So what we always do is we show little block diagrams like this. And generally in signals and systems, we call our input x of t. In electrical engineering, that's usually a voltage or a current, typically a voltage. It's a function of time. Then there's something that acts on it. Right? There's something called a transfer function. In this case, it's going to be h of t. Write down h of t. I'll get to h of t in a second. And the output of this system in the time domain, if it is a linear time invariant system, will be designated as y of t, which, and I'll get to this part next, is defined as x of t convolved, and the symbol for convolution is an asterisk, and I'll get to what convolution is next. So I got to write it down first. It's x of t convolved with the h of t, which is called the impulse response. Now I'm going to get into what linear systems are. This is the general way systems are actually described. Input is x, output is y. For a linear system, when a system is linear, it means if I put in, and I'm just going to assume this whole thing is a system. If I put in some x1 here, my output will be y1. Just give me that. Whatever x1 is, the output's y1. Forget about t for now. It's a function of time, but for now, forget about it. And if I put in some x2, I get an output y2. Now that should make sense. But for a linear system, it means if I put an input that was x1 plus x2, my output would just be y1 plus y2, knowing the two prior values. Understand? This is linearity. And you could expand this and you could say if you had an x1, x2, x3 that gave me y1, y2, y3, then if you had x1, x2, x3, you would have y1, y2, y3, and so forth, and just expand it out to infinity. With me? Now, that's a part of it. Another fact about linearity, if you have x1 give me y1, if I have ax1, it gives me ay1. Scaling, simply, 1 volt gives me 2 volts out, 2 volts gives me 4 volts, 4 volts gives me 8 volts, get it? That's a linear scaling. Got it, class? And if you had this one, if you had b times x2, you had b times y2. Got it? This is the basis for linearity in general. It also means if you have ax1 plus bx2, you would have ay1 plus by2. With me? It's that simple. That's linearity. I'm going to give you examples in a second. Now here's what time invariant means. This is generally true. Time invariant means that if I have a system where I put x of t in, and I get an output y of t, if I put x of t minus tau as the input, my output would be y of t minus tau. In other words, the instant in time that the system, the input is given, has no bearing on the output other than the output will track that input in time. Got it? So if you say t minus 1 is the input, x of t minus 1, the output would be y of t minus 1. With me on this, class? That's time invariance. Now, you need some specific examples of this to understand what I'm talking about. Here's generally a linear system. And this is a block diagram. I'm going to say x goes in here. My operator here is just going to multiply it by 2. So I'm going to put a 2 here. Wherever it comes in is going to be multiplied by 2. Follow me? Have you had block diagrams like this before? They say there's an operation there. It could be a multiplication by 2, division by 2, an addition by 2. It's something where inside that block it dictates what happens. It's the operator. Now the output here would therefore be y equals 2x. Right? Let's see if it's linear. I'm going to go two ways. I'm going to put an input here of 1. What is my output? 2. And if I put an input of 3, what's my output?
6.
6. Now, if I put an input of 1 plus 3 or 4, just take a look here. If I put 1 plus 3, now it's 4, I should just add these two up and get the output. So it should be 8, right? Well, if I put 4 in, 4 times 2 is 8. Do you all see that? It's the same thing as adding the 2 above. Got it? That means it's linear, right? Guaranteed it's time invariant because there is no function of time. So if it's not a function of time, it's got to be time invariant. Do you all follow me in this class? It's like a DC value. That's a linear system, the simplest thing. What's a nonlinear system? Well, tell me what you guys think about this. Suppose my operation now is, now it's going to take the input and square it. So I'm going to say y equals x squared. What's your gut feel? Is that linear or nonlinear? Nonlinear. What gives it away?
Square.
The squaring operator tells me if I put 1 in, right, I get 1 out. If I put 2 in, I get 4 out. Therefore, if I put 3 in, I should get 5. But if I put 3 in, I get 9 out. Follow me? That's nonlinear. Got it, class? That's it. And here's something that's not time invariant. Just so you see. I can think of a lot of things that have time invariant. Suppose I say my input is now just t. So it's time. And I'm going to say the operation is t squared. So my output would be t squared. Now, think about it. We just did the square operator, right? Well, if I put is this time invariant? Well, think about it. If t to here, right? What about t minus 1? What do you get as your output? T minus 1 squared, which is what? T squared minus 2t, right? Plus 1. You'll notice that this t squared, this is not time invariant. I don't want to go down that route right now, but you can see that really the skewing in time is something that's squared on. All right? And I don't want to spend much time on that right now. I can think of some other problems with going that route. But really, I guess that's not the best time invariant system. Let me give you probably the best. Suppose I said I have x of t here going in, and my multiplier here is really, I'll go Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. It's Monday, the multiplier is 1. Tuesday, 2. Wednesday, 3. Thursday, 4. Friday, 5. Saturday, 6. Sunday, 7. So on Monday, the output is times 1. Right? Y would be just the multiplier. Y is going to be equal to whatever the multiplier is times t. Now you can obviously see the day of the week determines the output's value. That's not time invariant. Follow me, class? All right. I think you got an idea of it. Don't worry about that part. I don't like to spend a lot of time on time invariance right now. A little bit later. All right. Now that I expose you to linear systems, and I think you have a pretty good idea. Anything built with resistors, capacitors, and inductors, any input-output relation there is a linear system. Follow me? Anything that's built with diodes, generally nonlinear. Generally nonlinear. Diodes, nonlinear. Anything that is built with linear amplifiers is linear, it's in the word. And anything's built with any kind of, well, I'm going to say it's called class, you don't even have this course yet, so I'm going to stop there. I don't want to get you confused. I just want you to appreciate we have to designate linear versus nonlinear systems in order to go ahead and do the engineering with them. If it's nonlinear, then the engineering is much different. But the basis is right here. Okay, now we're getting into convolution. So get a fresh piece of paper or something where it breaks this out. This is convolution. Convolution by far is, in my opinion, the most confusing subject. It's the most confusing subject you've run into so far. But I'm going to try to make this thing understandable. Now, based on the system perspective, stay on point here. We're going to assume I have some input x of t here. Or better yet, let's do it this way. I'm going to start with the most basic approach, the one that a lot of people use. I'm going to say, what if we put delta t into any kind of linear time invariant system? Oh, time invariant. I put delta t, that's an impulse function. What does an impulse function look like? This, right? That's what I'm putting in. My output is termed the impulse response. My y of t here would be labeled as h of t. And in here, usually I put LTI, but I'm going to go ahead and say h of t, because h of t is called the impulse response of the system. Just listen to me now. For any system, if I hit it with an impulse, the output of that system is called the impulse response. And it's not a spike in general. It's something that may have a very long duration. Now, I'll talk about causality. Remind me at the end of the class to talk about causality. Right now I don't want to. I'm just going to focus on this. So, keep that in mind. Now, if I look at this, input, output is h of t, called the impulse response. And you might want to write this down. This is the impulse response. All right. Now, I got to do this in a way that makes sense. Same system, but now my input is going to be x of tau times, I'm sorry, let me do it this way. If it's linear, if it's time invariant, if I put delta of t minus tau here as my input, what do you think my output's going to be, just by looking? It's a linear time invariant system. Class? H of
T minus
tau, right. H of t minus tau. Write that down. I didn't say some of this, but you'll figure it out. Now, for a linear time invariant system, if I multiply this by x of tau, now x of tau, remember this, that is like a constant value. Right? The system has an impulse response h of t, not h of tau. Got it? So we've displaced it in time by tau, and now I'm multiplying it by a function x of tau. It could be like x of 2, tau is 2. Got it? What happens to the output?
It shrinks.
Multiplied by x of tau, right? Good. X of tau. You're going to get this. You may not like it, but you're going to get it. You with me so far? Now, this is something that's always true with linear time invariant systems. If you integrate the input with respect to t, or tau, you can integrate the output. This, and I go from minus infinity here to infinity, the tau I come here and I integrate from minus infinity to infinity, d tau, and that is my output y of t, and that is the definition of convolution. Now I want you to just look at this and I'm going to explain something to you. Are you with me so far? Work the part, right? Delta t gives me h of t. You got to take that on faith for now. Delta of t minus tau gives me h of t minus tau, right? Then the input x of tau times delta of t minus tau gives me x of tau times h of t minus tau. You were with me so far, right? Now I'm going to integrate the input. The operation is integration. And I'm going to integrate not with respect to t, but with respect to tau. And I'm going to go from minus infinity to plus infinity. That means over here I've got to integrate the output from minus infinity to plus infinity. I'm saying that's y of t, and you're wondering why. And I'm going to show you. Look over here carefully. What did we say about the delta function? It does something very, very interesting. When we multiply it by another function and integrate it, what was that one thing that's very interesting about the delta function from last time?
The sifting property.
It sifts out the value, right, of the function it's multiplying when the delta function turns on or goes to infinity, right? When is that? When t is equal to tau, right? Or tau is equal to t, correct? Now, since the integration is in tau, that means what? This is going to become x of t. Are you with me? Dirty trick, right? So I pulled x of t out of this crazy integral that has x of tau times delta of t minus tau, d tau. Are you with me, class? My input is now x of t. And I say for any input x of t, my output can be found by taking x of tau times h of t minus tau d tau to get my output y of t. It assumes you know h of t. Got it? You have to know the impulse response for this to work. Are you with me? I'm going to take you through it, several things, and I've got to tell you some properties of this. This is the actual development of a proof. It's a little loose. I'm not going through every mathematical thing, and I'm not trying to rigorously show this works with linear time invariant systems, but I guarantee it does. Here's the general way convolution is written. If you have two functions, x of t and h of t, the convolution operator to get the output is normally given as x of t, and the symbol is the asterisk times h of t. This is the same thing as if you simply switch the actual position of these functions. So that's the same thing as h of t convolved with x of t. And the mathematical definition for this is the integral from minus infinity to infinity of x of tau, the first function, times h of t minus tau d tau. That's the mathematical definition. Now, this right here is a problem if you try to just mathematically execute that for functional forms. In general, it's always broken up into portions, and I'm going to show you how to do convolution graphically to get insight into it. I always like a picture, if I can, for any mathematical operation. That way it'll show me what's really going on. So I'm going to start with doing some convolution based on that mathematical definition and the way it's usually taught, and it's a graphical method. I don't think you've had this in your math courses. If you have, I'll be surprised. So I'm going to leave that up. Now listen, we're going to take two functions. And it doesn't matter the order that you take them. But generally speaking, the function that's got the most going on, you're not going to do anything and move it. Suppose I have x of t here, right? I'm just going to say x of t looks like this. I'm going to draw a graph. We can mathematically state this many ways. It looks like this. Here's one, here's one. That's x of t. Right? I can even put it here. It's a square box starting at 0, ending at 1, of height 1. Follow me? Now my second function looks like this. And I'll call this my h of t. Are you with me? This is t. Everybody? Now listen. The way you do graphical convolution is you pick the function that's got the most going on, and you simply start at the top, graph it, but not versus t versus tau. And here's why. You see the first operation here? The argument is tau. Got it? The integration with respect to tau. So I'm going to graph whatever the first function is, but not with respect to t, but with respect to tau. And the first function is the one with the most going on. By looking at that, which one of those two is it? Second one, right? The second one, I say the most going, it's got the most change. Do you all agree with me? So I come over here and I do this. Start there, and now I call this my h of tau. This is the same thing, by the way. Don't write this down as the integral from minus infinity to infinity of h of tau times x of t minus tau d tau. Doesn't matter the order. And I graph it, and it does this. And this is tau. Are you with me? Next, on the line down from that, you go to the function, this function here, but you do it, and you take, because look, here's what I'm going for. You see how I've got that I've got the second function, and the argument here is t minus tau. So you start with the second function with the argument of just minus tau. Listen to me now. So here's the first function, or I should say the first function. Here's my function, right? What does it look like if I had x of minus tau? Just tell me. And this is tau. Class? It would look like this, wouldn't it? Right? Isn't that x of minus tau? Y'all with me? Give me a show of hands if you see it. Think about what I just did. I've simply what? Changed the polarity, you might say, or the sign of the actual argument. And it just reverses it. Now it's starting at 0 going in the other direction. Agreed, class? Just right. So you start here, and this is x of minus tau. Now I'm going to add t to it. All right? Now I'm going to say I have x of t minus tau. Now, what happens is, the way you look at this is, where does this function end at, or start in a sense? When tau is equal to 0, right? 0, correct, class? Well, t minus tau is equal to 0, right? That means t is where it ends. Follow me? And this is called pulling the curtain. I like to say it's pulling this curtain this way, and this point is t. And this point, well, think about this. What is the width of this, class? 1. Therefore, whatever this is going to be t minus 1. Do you agree with me? Take a careful look. I know this is irritating. This would be x of t minus tau. How many see this? Come on. Just think about it now. What happens? What am I really doing? Y'all agree this is x of minus tau right here? Right? Y'all with me on this? Well, what happens when I add t to it? What do I need to do to figure out that function? Well, I know it ends at what? The argument here being 0, right? That means I set this to 0. T minus tau is 0. Tau is t. Got it? That means it's ending over there if t is greater than 0. Understand? But t can have any value at all. I just happen to choose one that's a little bit positive for my purposes. If it was less than that, we wouldn't worry about it. All right, now where does it end at? It's got to end at t minus 1. Do you agree? I chose the height to be 1 to make this easy. Now, what does the operation say? I take the first function, in my case, h of tau, and I multiply it by the second function, x of t minus tau, and I multiply these two, right? Now look here carefully. You all see that everything here is multiplied by 0. You all see that? So you don't worry about it. You only worry about, if this is t, this right here. When I multiply this by this, the net result is, and I wish I had a little more room here. Maybe I can shove it in here. Now if I have x of t minus tau times h of tau, when I multiply these two things, it's 0 to this point, then it comes up, and it ends here at t, and the height of this is t as well. Do you all see that, class? How many see that? And it's 0 everywhere else, right? Because think about it. The functional form here is, when you look at this, I've got 0 here, right? 0 times any value, any of these values is still 0, isn't it? This value's got finite values, this is finite values, so now I've got this. But then for anything greater than t, right, it's 0 out here. 0 times anything over here is 0. I'm not done yet. I have to integrate, right? I have to integrate from here to here, right? Because that's the only non-zero value. So now I can say, I'm going to do it over here. Erase this. So now I go ahead and I integrate this. And I say that my actual y of t here is equal to the integral from really, in this case, 0 to t of this function. What is the definition of this, by the way? Give me a mathematical statement for this. It's versus tau. Anyone? It's just tau, isn't it? Isn't it just tau? Right? It's a slope of 1, right? We're graphing versus tau here. So this height is tau. So now I'm going from 0 to t of tau d tau. What's that integration? Tau squared, right, over 2, evaluated from 0 to t, or simply t squared over 2, right? Now you'll notice when this is valid, this becomes critical. So I want you to just write this down. I want you to think about what I'm doing. You may hate it, but you will learn to accept it. It's like playing chess. If anybody's played chess, especially with somebody like a brother or sister that you had something against, or you were gambling or whatever, you always have to be very on point, thinking about every possibility. That's the way you have to think about this stuff. You can't do this with distractions and irritations and talking to a lot. It gets extremely important to be very focused. Are you with me so far for that part? But when is this valid? Think about it. Was it valid for values of t less than 0? Class? What happens? For t less than 0, this whole box is shifted down, right? And there's no multiplicative overlap between this function and that. It's all 0, got it? But it's good from where to where? For t being greater than 0, but
Less than t.
it's less than what? Less than 1. Remember, that's 1 and this is 1. Because here's what's going to happen. That box has a width of 1. When all of a sudden the entire box is in there, right? That's as good as it gets in terms of the coverage from 0 to 1. Then when you move out of there, all of a sudden now the trailing end of that box it's got a value of 0 here, right? So now we can say this is true for t greater than 0 or equal to 0, less than or equal to 1. That's always the case. Work with me on this one. Next, I wish I had some more time. Next, we do it for something. This was my h of tau here, right? And this is 1, this is the height of 1, correct, class? Now what I'm going to do is take this. I'm not even going to show you the x of minus tau. Now I'm going to go ahead and say this is t minus 1. This is the height 1, this is x of t minus tau, but now this is for t greater than 1, less than 2. In other words, here's 1. We're not, I call it the caboose. The back part of this hasn't moved out of the picture yet. Follow me? But the front part has moved out of the overlap. Here's what I mean. This part right here is being multiplied by 0. Got it? How many see this right here? Real important you stay on point. Now, what happens to the integration? The integration is still going to be what? The integral of this functional form. Thank goodness this has a value of 1. I just need the area there, don't I, class? How many see this? Okay? What's that area going to be? Now it's going to be y of t is equal to the integral, not from 0, but where? From t minus 1. Follow me? T minus 1. T minus 1 to where?
1.
Very good. 1, not t. 1, right here. That's where the area of overlap is between this function and this function in the tau domain. Got it, guys? Everyone? I really am doing my best, because if I'm sitting where you're at, I want to hear this over and over. Somebody beating it into me. What goes here? What's the mathematical statement for this function? Tau, isn't it? Wasn't it tau? That's why I say don't move that one. Because the one that's complicated, if you start moving it, now you're going to have tau minus some t or something, and you go nuts. You don't need to go nuts. So this is just tau d tau. And what do you notice this becoming? Integral of tau d tau is tau squared over 2. I want you to get used to doing that. Put down what the integration is. Don't do all the steps in your head. Put the limits. The limits are from t minus 1 to 1. Correct, class? Write them down, like I'm showing you. Understand? Hear me now. You're used to being very casual. Oh, that's tau squared over 2. And you'll put a 1 in there, so it's 1/2. You won't think about the lower limit. I've seen this too often. Be very, very formal with this part of it. Got it? Now with those limits, what does this become? That's 1/2. Now tau squared when tau is 1 is just 1, right? Minus, now it's going to be t minus 1 squared. Isn't it, class? Got me on that? How many see this? I pulled a half out in front. I didn't like it. Now what happens to this? That becomes 1/2, right? 1 minus the quantity. Go ahead and square it out. We have what? T squared minus 2t, right? Plus 1, correct, class?
Yes, sir.
What is that? 1/2 times, well, now I have 1 minus t squared plus 2t, right? Minus 1, correct, class? The 1 and 1 kills each other, right? And now I have 2t minus t squared divided by 2, right? So I have 2t minus t squared over 2. And you could pull out the 2. I mean, you could basically factor that, but that's essentially it. Do y'all agree? Let me do one more thing. If I pull a t out of there, and the 1/2, now I have this. I have 1/2 t times the quantity 2 minus t. Got me? Yeah. Oh, you don't have to. And this is good from t greater than 1, less than, help me class, 2, right? Because at 2, this would be all the way out, wouldn't it? Now there'd be no overlap. So this is from 1 to 2. And anywhere else in the time domain, for t less than 0 or t greater than 2, it's 0. Now if we're going to graph this briefly, let's do it. Now if we graph y of t here, 1/2, 1, 3/2, 2. Let's just do it. The first part, it was just what? This is now versus t, by the way. If we graph t squared over 2, what does it look like? It's between 0 and 1, right? Well, at 1, it would be 1/2. You agree with me? And it would look like this. Do you agree with that, class? That's a t squared, right? Times a half. From then on, what happens? Now when I have this one's a little harder to see. Well, look at this right here, just for a second. You're going to see the 2 minus t is bringing it down to 0 at t equals 2, right? But it's got this weight in front of it, t. It's hard to see this right away, but here's what it's going to look like. I call it a shark fin. It looks like this. That's what it'll look like. I was just down at Doppin Island. I tell you, once I get out in murky water past about here fishing, I start looking for any fins. I didn't see any of these, but I was looking a lot. I have been in the water with sharks, and I don't like it. Are you with me, class? That is a trivial example of convolution. They get much, much harder. I'm about out of time, man.
Yes, sir. You're out of time.
Do me a favor, class.